Good morning, students. Let's talk about the development of shear force and bending moment diagram when there is a uniformly distributed load. I am directly starting off with the question in which, let us say you are having a simply supported beam. This beam is subjected to UDL, uniformly distributed load, upon some span. Okay, so the value of UDL is 3 kilonewton per meter. This span is 3 meters, 2 meters and 2 meters. So the total span of the beam is 7 meters. See, what is UDL? UDL is uniformly distributed load. Distributed load. It means the load that is of some value that remains constant for a given length of the beam. For example, in this case it is 3 kilonewton per meter. UDL will always be given in kilonewton meter and it is acting on a span of 2 meters. So the total load is 6 kilonewton. 3 kilonewton per meter for a span of 2 meters, that is the total load is 6 kilonewton. And when calculating the bending moment, it will act at the CG of this particular section. So CG means, because it is a rectangular kind of distribution, the CG will lie at the center. So it will be supposed to act at the center of that particular load. Okay. So in this case, if we want to draw the shear force and bending moment diagram, the first thing is again calculating the reactions. So I am taking this as RA, this is B, C, D. So this is RD. So in order to get the reactions, I will take moment at point A equal to 0. So what will be the moment equation? RD into 7 minus 3 into 2 is the total load. Where is it acting? It is acting at its CG. So what is the distance from this particular point? It is 3 meters plus 1 meter, that is into 4 is equal to 0. So you will be able to get the value of RD. So RD is coming out to be 3.43 kilonewton. Then I'll apply summation Fy equal to 0. Summation Fy equal to 0 means RA plus RD, this is equal to total load that is acting. So total load is 3 kilonewton per meter plus 2. So it means 3 into 2. RD is 3.42. You will put the values, you will get the value of RA. Its value is 2.57 kilonewton. So RA is 2.57. RD is 3.43. Okay. So the next thing is, now in order to draw the diagrams, I will have to divide this particular beam into number of sections. You will have one section AB. Then at B point there is introduction of this load. So from B to C the load is continuing. So the second section is from B to C. The third section will be from C to D. Okay. So section AB. Next section is section BC. And the third section is section CD. So what is happening in section AB? I will cut it at a distance x from here. Okay. So for section AB, the FBD will be 2.57. The section has been cut here. It is the right hand side of the section. So positive shear force will be down. Positive bending moment will be anti-clockwise. Similarly for section BC, I will cut somewhere in between here. I will cut somewhere in between here and at a distance x. So my section will become 2.57. This is the load. This is x distance. The load has been 3 kilonewton per meter, but it has not come on the complete span. So this is positive shear force. This is positive bending moment. This is 3 meters. The third span I will cut at this particular point. I will again draw the free body diagram of this side. This is 2.57. Now the load is completely come. So this is 3 kilonewton per meter. This span is 2 meters. This is positive V. This is positive M. Okay. So this value is X. Let us quickly write down the equations for shear force and bending moment. For the first section, what will be shear force? Summation Fy equal to 0, that is 2.57 minus V is equal to 0. So V is constant 2.57. Write moment equation equal to 0. So I will write down the moment at this point equal to 0. So moment equal to 0, my equation will be 2.57 into x is clockwise minus m is equal to 0. So m becomes 2.57 into x. Is it okay? So your shear force in this particular section is constant. So this is constant, whereas moment is linear. Okay. Now coming to the second section. Again I will write down summation Fy equal to 0. Your equation will become 2.57 minus 3. Now this is 3 meters, this is x, so this distance will be x minus 3. So 3 into x minus 3 minus v is equal to 0. So v becomes 2.57 minus 3 into x minus 3. Similarly, we can write down the moment equation at this point equal to 0. So moment will be 2.57x minus 3 into x minus 3 is the load. So it will be acting at the CG. So what will be the distance from the right hand side? X minus 3 by 2. So it means this is square divided by 2 minus m equal to 0. Your m becomes 2.57x minus 3 into x minus 3 square divided by 2. So it indicates the shear force in this section is varying with respect to x. So it is linear. Your bending moment is varying with respect to square of it. So it means it is parabolic. So it is parabolic. Okay. Coming to the third section. Again, summation Fy equal to 0. Your equation will become 2.57 minus 3 into 2 because the complete load has already come. Minus V is equal to 0. So V will become 3 minus 3.43. So it means shear force is constant in this section. Coming to the moment equation, I will be writing down the moment at this point equal to 0. Summation m equal to 0. 2.57 into x minus 3 into 2 is the total load. 3 into 2 is the total load. It will act here. Okay. So it means this is 3 meter has already gone. 1 meter is gone from here. What will be the distance from this side? X minus 4. Okay. So x minus 4 into x minus 4 is equal to m. So your moment equation, it indicates that it is varying with respect to x only. So shear force is constant, bending moment is linear in this section. Okay. Based on this, let me draw the shear force and bending moment diagrams. So your beam was this, 3 meter, 2 meter, 2 meter. This is 3 kilonewton per meter. What is shear force? I will draw a zero line for shear force. This reaction was 2.57. This reaction was 3.43. Okay. Shear force will start at 0. It will have a sudden increase. Why there will be a sudden increase? Because there is a point load kind of thing upward. So there will be upward shift. Then from A to B, there is no load. From A to B, this equation indicates that your shear force is constant. The value is 2.57. So I will draw a constant line 2.57. Okay. Then from B to C, your shear force diagram indicates that it is linear variation. Okay. It is linear variation. So it means what is V at the starting, that is, okay. Let me just give the values of x also here. For A to B, the x will vary from 0 to 3 meters. From B to C, x will vary from 3 to 5 meters. Okay, 3 to 5 meters. For CD, x will vary from 3 to 7 meters. Okay. So when you are saying BC, you will put x is equal to 3 here. X is equal to 3 here. In this equation, your V at x is equal to 3 becomes 2.57. Okay. Similarly, you will find out V at end of the section, that is 5 meters. Put x is equal to 5. Put x is equal to 5 here. You will get the answer of minus 3.43. Okay. So it means it will start at 2.57. It will end at minus 3.53. In between, the variation is linear. So this is 3.43. After that, your shear force diagram for the next section is minus 3.43 only. So it is constant 3.43. And at the end, the check is there must be a reaction of 3.43 to bring the diagram back to 0. So your shear force diagram is positive in this section, negative in this section. Positive means in this particular part, the beam will experience a system in which left hand side will try to go up and right hand side will try to go down. Whereas in this, it is the opposite. Okay. Okay. So next thing is drawing of, this is SFD. Next thing is drawing of bending moment diagram. For drawing a bending moment diagram, again we will mark a 0 line. We will see that from AB, what is the variation? For AB, the variation is, see the diagram indicates it is linear. So what is the moment at start of the section? We will put x is equal to 0, it is 0. What is the moment at end of the section? That is x is equal to 3. We will put x is equal to 3. Your bending moment will come out to be 7.7. Okay. So what we will do is from 0 to 7.7, we will have a linear joining. So this is 7.7 value. Now, we know that from B to C, the variation is parabolic. Okay. We will get the value of bending moment at start of the section, at end of the section. Along with that, we will have to find out this point. Why this point is important? Because over here the shear force is 0. So this will be the point where the bending moment will experience a maximum value. Okay. So how can we get this point? We can get this point by making this shear force equation of the second section equal to 0. So what I am trying to say is I will make this 0. Okay. So it will be 2.57 minus 3 into x minus 3. This is equal to 0. You will solve this. The value of x will come out to be 3.85. Okay. So what I will do is I will put moment value at this particular. So what is for span BC? The moment equation is 2.57x minus 3 into x minus 3 ka square divided by 2. I will get the value of moment at start of the section, that is moment at x is equal to 3. The value will be, you will put x is equal to 3, value will come out to be 7.7. I will get the moment at end of the section, x is equal to 5. The value will come out to be 6.83. I will also get the value of moment at x is equal to 3.85. Because this is the point, this is at a distance of 3.85. So this is the point at which your bending moment is going to be maximum. So 3.85, I'll put the value, I will get the answer of 8.8. So at this point the moment is 7.7. At this point the moment is 6.83. At this point 3.85, the moment is 8.8. The moment is 8.8. So I will join these three with the help of a parabola. So this value is 8.8. This value is 6.83. Okay. Now the next thing is, in span CD, your bending moment is only varying with respect to x. So moment is linear. Okay. So the moment equation for span CD is moment is equal to 2.57x minus 6 into x minus 4. I am taking this equation from this particular point that I had already calculated. I will get the moment at start of the section, that is at x is equal to, CD will be 5 to 7. X is equal to 5. I will get the answer of 6.83. I will get the value of moment at x is equal to 7. I will put x is equal to 7 here. I will get the answer 0. So it means for CD span, the bending moment is varying from 6.83 to 0 and the system is linear. So this is linear joining. Okay. So your bending moment is all positive here. Bending moment is all positive indicates there is the sagging moment throughout the span. So throughout the span, the system is moving like this. Is it okay? So this is drawing of shear force and bending moment diagram when there is a UDL. You can see shear force diagram and bending moment diagram, they are following those basic rules. It starts from 0, it ends at 0 in both the cases. If there is no load, this is constant, this is linear. If there is a UDL, shear force diagram is linear, bending moment diagram is parabolic. Then for CD, there is no load, shear force diagram is constant, bending moment diagram is linear. Okay. So I hope that you will be able to do shear force, you will be able to draw the shear force and bending moment diagrams wherever there is a UDL. Kindly try on your own. If there are doubts, you can easily comment on it. Thank you so much.